videos. I would support that. Okay. So some announcements. So final Wednesday, I've posted a practice homework assignment on Blackboard. So this is not for credit. I don't want you to turn it in. I mean, you can't turn it in. So, but these are example Lambda Calculus questions that we haven't covered yet that I've used previously on homework assignments. So you would have got this homework assignment if we were a little bit ahead. And also some Lambda Calculus questions from last year's final. So I think they would be definitely worth your time to study. Questions on that? There's a large amount of people in here for a project being due today. Is that a good sign or a bad sign? Interesting.
Yeah, but have you seen the other times?
All right.
There's like 6 people.
Be a solution set posted for that practice homework at some point before the final, or?
I don't know.
Okay.
I don't think so. I can probably do it, but I'd rather you guys.
I don't know if we do it right.
By working with each other and comparing answers and knowing what's right and what's wrong.
See, the knowing what's right and what's
That's
wrong
all
is the
well
hard
and good,
part.
except that finals week, like, there's no guarantee that we have the same time off for the people we usually work at.
I see. Yeah, I'll probably do it, let's say next Monday. Let's shoot for that. I'll be able to post at least the solutions. Okay.
Thank you.
Cool. You're welcome. All right, so we're talking about Lambda Calculus. We're right at the tail end here. There's actually just one concept that I discussed a little bit on Wednesday that we absolutely have to get to, if only because if you take Lambda Calculus and you don't learn about the Y Combinator, then you really haven't learned or taken Lambda Calculus. It's one of the fundamental concepts. But first, before we get there, I want to talk about Boolean Logic. So we're going to do logic, maybe touch on addition slightly, but we're going to definitely get to recursion. So we saw that the way we're going to handle Boolean logic is we're going to define a truth value and a false value, right? These are incredibly arbitrary. I mean, not incredibly arbitrary. By defining true and false like this, we actually get, and correctly defining and, or, and not, we get the proper behavior, but true does not have to be in this way, and false does not have to be this way either. Just like in a programming language, right? Some languages, 1 is true and 0 is false. Like in C, there is no Boolean. Or actually, it's more like 0 is false and anything that's not 0 is true, right? Whereas in other languages, sometimes an empty list or an empty string can be false, whereas anything else is true that's not 0 or false or an empty list or an empty string. So it really depends on the language. Okay, so we saw that, right? We have an and. We can define and like this. So and, just like our normal and function, right, takes in 2 parameters, a and b. And what it does is it applies a to b to f. So let's think about exactly what this does. So we talked about, okay, and should only return true when? When both a and b are true, it should return true, right? Okay. So let's think about this. Let's just look at this here, right? So it's going to be a, b, f. So the first parameter applied to the second parameter, and then f following it. So if you think about what happens if a is false. So remember, what did true return? It takes in 2 parameters. What does true return?
The first parameter.
The first parameter. What about false? Second parameter. So that's the way to think about them. You can mechanically do the beta reduction here, and you'll get the correct answer. But trying to develop some intuition for why these things actually work. So if a is false, then what's this going to return? False. It's going to return the second parameter. Does it matter what b is? No. Right? Just like in an and condition, if the first parameter is false, it does not matter what the second parameter is. Okay. So then what's the other case? So a can be false, and we know that it's going to return false. What's the other case?
It'll be true, so it'll look at me.
A is going to be true, so what's it going to return? A ABF, if A is true, what's it going to return?
F applied to B. Other way around.
Not quite.
Damn.
So you think of it like functions, right? If A is true, it takes in two parameters, and what does true return? The first parameter, just the first parameter. So it's going to return B, and so now does it matter what the return of AND is if what B is? So in that case, if A is true and B is false, then what's the return of the AND function? False, because it's B. And if B is true, then what's the return of the AND function?
B.
True. Yeah, so we have the case and true, true, if we call this function, right? And here we're using mathematical definitions here, right? We can completely fill out we can write this entire lambda expression without any of these names. So this is going to expand to lambda b dot ab applied to lambda x dot y. Is that right? And I feel like I'm missing a t. All right, let's look at it here. So we can actually step through this. So yeah, on the left we have the and function. Ah, yes, this is false. Okay, yeah, that makes sense. Where did this come from? Yes, this is the false inside the and function, right? So this is the whole written out and function, right? With no names, no anything. So think about this. Can we beta reduce this and function? As it is. How do we tell? Yes, expression, and specifically what has to be true about those expressions?
Where the left expression is lambda.
Where the left expression is a lambda, exactly. So we have function applications here, and we know from the precedence rules this technically is going to happen first, and then this is going to happen. But are any of these rules where the left is a lambda abstraction? Let's take it like this. AB, is there a lambda there?
No.
On the left? No. And if we take AB applied to this, is AB like this a lambda on the left? No. So we can't beta reduce this function anymore, right? It's just a function definition. Okay, now let's do the whole thing and walk through it. So here we're trying to and true. So what should be the result? True. That's where we want to go. Right? So here, right, first I'm going to do, we know based on the precedence rules, right, now here we have application, expression, space expression, where the left side is an abstraction. So now we can do beta reduction step here by applying, essentially calling this function with this parameter lambda x dot lambda y dot x. So we're going to use the exact same techniques we already learned about. We're going to change this. We're going to, inside the body of this abstraction, we're going to substitute a for lambda x dot yx. Right? And so this is replace every free a with lambda x dot lambda y dot x. Right? And so the thing we have to think about, are there any free variables in what we're replacing? No free variables. So we don't have to worry about doing any renaming. Right? We only have to worry about renaming if what we're substituting has some free variable. So you can think about what we're substituting in here is completely self-contained. Right? It has no global references, so it doesn't matter where we put it because any variable that it refers to is contained within that lambda expression. So we replace this a with lambda x dot lambda y dot x. Right? So now at this point, we actually do have a choice between what kind of application we want to do, right? So there's the outer application. Is the left-hand side of this outer application a lambda? With the two expressions? But then what about this application here? B applied to lambda x dot lambda y dot x, space B. Right? That's another another place we could invoke a function. So we can actually do either one, but we'll continue in the way that we were doing it by doing the outer one first. So here, once again, I'm the body of this abstraction. I'm substituting in B for whatever was on the right. And once again, any free variables here? No, so it makes things very easy. I just replace every free B in here with that exact expression. If I do that, now I have this lambda x dot lambda y dot x, lambda x dot lambda y dot x, lambda x dot y dot x. Right? So if we look at the behavior, what we think this function should do, right? We know this is a function that takes in two parameters and returns which one? The first one. So it's going to take in two parameters and return which of these guys? The first one. And what is this value? What did we define this as? True. So it's going to eventually return true. Right? But we can actually see this mechanically how this works. So we're going to do this application. We're going to, inside the body of this abstraction, we're going to set every x equal to this parameter. Right? So we're going to use our substitution operator. We're going to substitute every free x in here with this expression. Once again, there's no free variables here, so we don't have to worry about renaming. Right? Why is that? Because we have a lambda y here and a lambda y here. Isn't this going to cause problems?
No, because that function's lambda y.
They're meta variables.
They're that function's y, not a global y.
They're meta variables, so it doesn't affect anything anyways. But even if there was a y in here, that y inside the substitution always refers to this lambda y here, right? This meta variable. It doesn't matter where we put that, because wherever we put that, this lambda y is going to be outside, right? So the scoping rules mean that we're not going to accidentally refer to that. This is kind of what I mean when that expression is self-contained, right? No free variables. So every relationship between a variable here, x, and a meta variable, that binding is constant, right? We know exactly what that is. And it's not going to change when we do this substitution. So we substitute x for this. So we have lambda y dot lambda x dot lambda y dot x. So we have one more application. So we're going to substitute in here y for lambda x dot lambda y dot y. So what's going to be the result of this?
Our defined true value.
Yeah, right? This here, are there any free y's in here? No, so the substitution operator doesn't do anything. Essentially, we've gotten rid of this parameter. Right? It goes away. And now we're left with this, which is true. So the idea here is it makes sense kind of when you look at the function, right? When you look at the definition of and, it was AB true, or AB false, right? By kind of reasoning through the ways we defined true and false, we saw that, okay, yeah, that makes sense. But if you apply, mechanically like this, and just do the derivations, you should get for true and true, true. And then just like when you build truth tables, right, in architecture class, you could do this for every combination. You try false, false, make sure do this, it returns false. You try true, false, make sure it returns false, and you try false, true, and make sure it returns false. Right? So let's look at one other different case of true and false. Right? So essentially here, we kind of already saw what's going to happen. Right? Just like before, if the first parameter is true, we will return b. So whatever b is going to be the return of our and function, which in this case is going to be false. So we can do it at a little bit of a high level here, where we don't actually fill out all of the names, right? We actually know, okay, we can replace a with t, right? And we know that t is a combinator. It's completely closed. So we know we can do this without having to worry about any names, right? So we can replace a in here with t. We can replace b then with f. And we can say, well, what does true, false, false do? Well, let's expand out true because we know it's a lambda. So we know we can do something here. So now here we replace x with f inside here, and then we replace y inside here with f. And we know here that this f, once again, is fully contained. So there is no free y. There are no free variables in f. Right? So we know that this does nothing. And then we get back f. Is this a lot easier to think about than the detailed one? But it is the same, right? At the end of the day. Right? These are it's the exact same diagram, but replacing all of these with either falses or trues, depending on what their value was. Questions on this? And then we can look very quickly at, we can kind of already see where this is going, right? We can see and false true. Right, so because this first parameter a is going to be false, we will always return the second value here. And that second value is that constant false that we put here in this function. And so we know just by looking at this, right, that, okay, a will be replaced with f and b will be replaced with t. So this is going to be equivalent to f, false, true, false. And so we said false always returns what? Second parameter. And so it's going to return false. And similarly, right, so it's just being thorough, we're going through all of these. We have and applied with false, false. We get triple false. This first false always returns the second argument, which is false, which means we're good. So do you believe that this is a Boolean, what we just defined an and operator, and at least part of Boolean logic? I guess we technically have to do, I think, what is it, NAND is complete. You can do every Boolean operation using combinations of NANDs,
Yeah.
right? But not just and. I think you need something else, right?
Wouldn't you also need or and exclusive and?
I think you can build up all of those from NAND. Like if you just had NAND gates, you can build any arbitrary logic. But I don't think the same holds for just and. We have to do crazy combinations. So let's do a not operator, right? So what should our not operator look like? What do we want? So let's think about, we're defining functions, right? What do we want this function to have? What's the signature of this function?
If something's true, return false.
And then,
If something's false, return true.
so how many parameters does it take in?
One.
One parameter and returns one parameter, right? So we want something like this. Not true returns false, and not false returns true. Right? We want to not, this is our desired input. This is not the definition, right? So how can we write this? There is no magic. That's going to be the theme. I'm going to destroy your sense of wonder. Alright.
Do we have to do it in one definition, or can we use two different ones?
What do you mean? You like have an if statement, like if t, then return false?
Kind of.
It's essentially what we want, but we kind of already have that. I mean, so we want to find some not, right? We know that not, when we give it true, should return false, and we know that if we use not and we pass it false, it should return true, right? So how many parameters do we say it needs to take in?
One.
One. So let's say we know already that it's going to be something lambda a dot body, right? We know it's only going to take in one parameter. So what is it going to take in? So what was the trick that we used in defining and?
You knew that it would only continue if it resulted in true, but then it would check the next one.
Yes, we knew the behavior of the true and false functions, right? We used the fact that, thinking about it like an if statement, right? True means takes in two expressions, arbitrary expressions, and returns the first one if it's true, but if it's false, it returns the second one. So almost implicitly here we have kind of branching built into our Boolean functions, right? So if we do a here, so a is either going to be true or false. So if it's true, then what's going to be returned? we want to be returned?
False.
False. So for A, which parameter is going to be returned? When we call a truth value, if it's true, which of the two parameters is going to be returned?
First one.
First one, so what should we put right here after it?
False.
And then what after it?
And then true.
And true. Right? So here, if A is true, it will return the first parameter, which is false. And if A is false, it will return the second parameter, which is true. And so we've basically built this if A,
False.
yeah, so if A false, else true is essentially what we're doing here. And by creating the true and false values, I mean, this is where why I say you can't just define them arbitrarily, right? But we get this if behavior, right? We get this choosing or deciding between two branches in some sense, right? Because these values that are here, right? Here we're using false and true, but they could be any expression, right? And any expression can be essentially any program, right? This expression here, I'm trying to argue that these expressions can be arbitrary lambda expressions. And true will choose the first one, and false will choose the second one. So you have implicit branching there inside the way we define true and false, which is super cool. So yeah, we can see that not true is going to do true, false, true, which will return false, and not false will return false, false, true, which will return true. It's exactly the behavior that we wanted. Right? And we actually, as I alluded to, right, if we want to do like an if condition of if some condition do A, otherwise do B. So we want if true then A, otherwise if false then B. Well, we already have that. True and false already do that, so we actually don't even really need an if function. Right? I mean, we can define an if function that looks something like we're used to, if condition A or B. But this just returns whatever the first parameter is, C. Right? So if it's true, then it will return A. Otherwise, if it's false, it will return B. It'll do any beta reduction that it needs to do there. So we have basic branching operations. So we have if true AB. We have our if we're defining as essentially the identity function, so it returns its first parameter and only parameter. So when we return this, we're going to get tab, and that's going to return A. And if the condition is false, it's going to return fab, which is B. Right? So here we have a super basic if condition, but we don't actually, the if condition's not really doing anything, right? It's the Boolean logic here, the way we define true and false, that's doing this. Okay, questions on logic? So you convinced logic is possible?
No.
No?
Witchcraft.
Witchcraft? You're probably in the wrong major then. If you think logic is witchcraft in general. What about specifically this logic? Yeah, so you could do any arbitrary logic here, right? Anything. So we did and not, so we know it's complete. Very similarly, you could define XOR functions, you could define OR, any logical operator you want, you can define using Lambda Calculus and using these true and false values. You can change how you define the true and false values and define a whole different system of logic, but it can still work the same way. Okay. All right. I'm going to skip ahead. I really want to cover numbers. All right. How important are numbers anyways?
I'm pretty sure they're pretty important. Just depends on if they're on the
Still need to
finals.
learn those.
Just logic? Yeah, I don't know. Okay, let's do this. We'll go over numbers very quickly. No. We're going to do... Okay, because we just did logic, right? We did logic, and we can do true-false branches, right? So already, if we can do logic, we can do true-false branches. We pretty much have most of our language, right? Just like a Turing machine has a program, and depending on what symbol it reads, it can move to a different state, right? So that's essentially a branch, right? Just like here, we have a branch, we define an if statement, which will choose between two different expressions. Okay, we will have arithmetic, where we can do numbers, we can compute on numbers, but just like a Turing machine doesn't have any intuitive concept of numbers, right? It only writes out ones or zeros. Very similar thing here. Is that arithmetic spelled right?
Yes.
Okay,
Yes.
weird. It looks weird. All right. Just like that, right? We're going to do it in a different way, just like we did with true or false with using functions to define the numbers, which is very similar to using ones and zeros to define numbers, right? Just different ways of encoding that information. But are we actually Turing complete with this? If we have branches and we have arithmetic, are we Turing complete? Can we do everything that a Turing machine can do?
Yes.
Yes? Are you just shouting out an answer?
Yes.
Yes. Are you just repeating the same answer again? Well, think about it. I mean, this actually gets to something very big. This is why you are computer scientists and not getting a degree in programming, right? Because you're thinking about computation, right? What does it actually mean to be able to compute something, right? Can you write a program with just branches and branches and arithmetic?
Don't you need go-tos?
Why do you need go-tos? What specifically do you need?
Well, just looking back at the project definition that you need go-tos to go back up to. I mean, you can make everything with ifs and go-tos.
But what do go-tos allow you to do?
Go-tos
allow you to repeat parts of code.
Yeah, to loop, right? And to loop an undefined number of times, right? Exactly. So that's what we're missing here, right? We have no loops. We have no way to execute something again, like to do an instruction again here, right? Think about a program, writing a program that just does branches and has no way to go back is actually not a Turing complete program. I mean, that program is fine, but that language is not Turing complete, right? You can't write a program in that language to do something like, how do you calculate a factorial? Right? Could you write a program that takes in a number and calculates a factorial with only branches and arithmetic?
No.
For a finite size, yes.
Exactly. You can only write it for a finite. You could have all these huge if conditions of if n is less than 10 or whatever. I mean, you could write out all the cases, but you can't handle the general case of I give you a number n and you give me factorial of n. Right? So factorial of n, we have our base cases, right? We have factorial of 0 is 1. Factorial of n is n times factorial of n minus 1. Right? And so if we're writing this in C, like we've been studying this whole semester, right? If we define a factorial function, we check. If the factorial is 0, we handle the base case, right? We always have a base case. If it's 0, we return 1. Otherwise, we return n times factorial of n minus 1. Right? And this follows very similarly to the mathematical definition of what a factorial is. What kind of a definition is this mathematical definition here? Recursive. Why is it recursive? What does that mean?
It includes its own definition in its definition.
Yeah, it calls itself, right? It's terrible in a dictionary. You don't want to define a word with itself, right? But here, it's one of our basic primitives that we use in programming. We want to be able to call the same function with itself. Okay, so assuming that we can do addition, we can do multiplication, we have a way to do those, and assuming that we have an is0 function, so some function that tests if it's 0, and we have some way to do n minus 1. So in this case, we're going to call that the predecessor, or the pred function, right? So every number has a predecessor and a successor, right? So it's that number minus 1. Right? So if we wanted to follow this definition that we have here, we'd want something that looks like this, right? We want to say factorial, and it takes in one parameter n, so we have lambda n. Then we have our if, right? And so what's the condition of our if? Well, if n is 0, if that's true, return 1. If it's false, multiply n with factorial of n minus 1. Everyone agree that this is the straightforward application of that program we just wrote in C? But what's the problem here?
Wouldn't you have to like put the definition of fact in there and have it like expand out?
Yeah, we've been using equality, right, by saying true is this. We're using the mathematical definition where we're saying true is defined as this, which means everywhere we see true, we can replace it with this. Right, so we can always get rid of every name that we've ever seen. We can get rid of if, we can get rid of is zero, we can get rid of mult, we can get rid of predicate, right, and write out their exact lambda expressions with no names. But how can we do that with factorial if it's used inside of its own definition?
It would just expand forever.
It would expand forever, just like the type system, right? And it would never actually be able to build a concrete type. We'd never be able to have an actual function here. So we cannot write this function in this way. But the crazy thing is, this does not mean we can't do recursion in lambda calculus. And this is actually an idea that's pretty insane. So you want to be able to call a function, but you don't actually have a name of that function, right? This is an anonymous function, right? Factorial has no name. We cannot refer to it by name. But we can still get recursion here. And so it comes back, so I mentioned about combinators, right? No lambda expressions with no free variables, right? There are actually a bunch, alphabet soup of combinators. One of them is the Y combinator. Anybody notice that term from another context?
You mean combinator?
Huh?
You mean the word combinator?
No, Y combinator, that specific expression.
Nope.
No?
No, there's a.
No startup people or
Yeah,
entrepreneurs in the
there's a
audience?
Website or something? Like a startup.
Yeah, they're a startup incubator in Silicon Valley. They were started by some people who founded an original company called ViaWeb in the early .com in like '98, where they created, they built a website, like people could create automatically their own online stores. It's called ViaWeb, and they got bought by Yahoo for a bunch of money, and that became Yahoo Stores. Then they decided that they wanted to get into startup investing, and so they did but they didn't want to go the VC, the venture capital model, so they did this they were the first ones to do this incubator model of, you come for the summer, we'll give you, I don't know, $10,000 or $20,000 for X percentage of your company, you'll work fully on your startup, we'll give you access to our network, everything, and then you can, then after that, then you go out and get money. So it's like trying to fill the gap in between you're self-funding your startup and when you get big, like multi-million-dollar venture capital. Anyways, they're incredibly successful. Airbnb, maybe you know about them. Dropbox. Those are all Y Combinator companies. There's actually a huge list of Y Combinator companies. So that's what they named their startup incubator, is Y Combinator. And it is directly from Lambda Calculus. So if you are ever going to try to get money from these people, you should definitely be aware and know what this is and how it relates to programming. So we're going to find this combinator kind of crazy. So the Y combinator is lambda x dot lambda y dot y applied to xxy. And on the right we have lambda x dot y xxy. Yeah, so it's the same thing repeated, right? The question is, what does it do? So let's say we're applying this to something foo. So we have the huge lambda combinator, the Y combinator. We have foo, right? And so let's do this first application, because we actually have an inner application inside the Y combinator, right? So we have the application of this to this. So how many parameters is this one going to take? Two parameters. So what's it going to do with the first parameter?
Discard it.
Replace x's.
Replace the x's with this. The x's x's are twice, right? Notice how the y combinator has 2? So this is essentially propagating the y combinator here. These x's are going to be replaced with 2 of this parameter, which is the y combinator. So this will be the y combinator again. And so foo is the second example. So what's going to happen with foo?
Replaces
It'll
y.
be thrown in for y.
It's going to be replaced with y. So we're going to have foo here. But what is this xxy in here?
It's the Y
So,
combinator
yeah.
again here for
It's not exactly, it is the y, the x's are the y combinator, but what's the y here?
Foo.
Foo, which is this, what we started with. And then what happens if we expand that again, the xxy?
We continue and continue.
The exact same thing again. So we're going to do the replacement, replace all the x's in here that we saw. So these x's are all replaced with this guy. We have foo. Then we replace all of the y's with foo. And so we end up with foo applied to y foo. But is this foo a name?
Yeah.
No, it's not a name. It's a lambda expression, right? That lambda expression gets copied there. And then what happens when you expand this out?
Y foo again?
You get y, you get foo y foo. And then inside there you get foo y foo. And then inside there, foo y foo. Right? Does it ever stop?
No.
No. So we get,
It stops when foo has some kind of base case.
yeah, so we have to code it correctly so that it has a base case so it doesn't continue forever like this. But here we're getting a function to basically keep calling it out, calling itself, right? We've essentially done recursion here using this crazy y combinator. So what we can do is we can actually define our factorial function. So instead of like this, right, where here we can't actually write this definition even though this is what we want, right? This is our goal state. This is what we want the factorial function to be. But what we can do is if we set the factorial function first to return y, the y combinator applied to that function that we want. But what changed about the function?
It's now f instead of factorial.
Right, but how many parameters does this new thing have in here? 2, right? So what are we passing in as the first parameter here? Itself. Exactly, yes. The function that we want to call is going to get passed in as a parameter, and the y combinator will make sure that what gets passed in is going to be this function again. And then if we call f on predicate of n, we'll do predicate of n, and then we will do this again, and it will expand again until we hit the base case where is 0 and we'll return 1. So by changing this, by saying, okay, we cannot name factorial, but we can accept it as a parameter. We can call a parameter f, and we can put it as part of an application here. So let's see what this looks like with factorial of 1. So we have the y combinator applied to this guy, which is the one we originally want with another parameter, applied to n. Or, sorry, applied to 1. So we do the y combinator step, which first gives us lambda f dot lambda n, so that the expression that we passed in, right, applied to y of lambda f dot lambda n is size 0, 1, multiply n by f, predicate of n, 1. Expanding that out again, so replacing now the f with the new function including the y, right, the y combinator. We can reduce f, we can replace all the f's in here. So now we have something that we can reduce. We have an n and we can replace it with 1. And so we say if 1 is 0, return 1, otherwise multiply 1 by y of the same thing again. Right? 1 with that, y applied to this same thing again. we do this again. We say is 1 0? No, it's false. So it's going to return the second argument here. So it's going to get rid of this first one. So we have multiply 1 by whatever y of f of n applied to the predicate of 1. So we go through the same steps again. That's going to go out, give us here where we now have our y combinator inside here. Now we have the predicate of 1, so we replace n with the predicate of 1. Predicate of 1 is 0, so we're going to replace n with 0. Now we have, is it 0? Yes, it's going to be true. So we will, this whole thing, now we are not going to evaluate the false branch, so we don't care that this is going to repeat infinitely, right? Because it goes away. It's like an if statement. Here, the statement is true, so we take the true branch, which is 1. And so this whole thing reduces to 1. You multiply 1 by 1, you get 1. So now we have Boolean logic, we have arithmetic, we have loops, we have hit Turing completeness. But do we actually have numbers? What? I just lied to you. Okay. So what we're going to do, we need to define, just like we did true and false, right? We're going to try to define each of the numerals to define 0 as, well, actually, how many parameters does 0 take in? 2. Which parameter does it return?
The second one.
The second one, which is similar to what? False. False. Yeah, so we actually define it the same as false, which is kind of cool. We define 1 as lambda f dot x of f applied to x. Can we do this?
Yeah.
Sure, why not? And so we'll define the numbers based on whatever number you give me. I will apply f that many times in the body. So 2 will be .ffx, 3 will be ffx. Can we do that? Sure. Is there any difference between encoding numbers like this versus ones and zeros? You can actually, well, you can do numbers with all ones, right? I mean, you don't actually have to have a 0. It makes it more efficient. Or you need to have a way to distinguish between a 1 and there not being a 1, but you don't actually need a 0 character, right? And 4 would be 4 f's. And so the way to parse this is we first apply f to x. We apply the result of that to f to f to f, repeated infinitely. So the idea is if I have 4ab, this is going to result in a, right? The first parameter being done 4 times. So I have numbers, right? So I have some concept of numbers so that I can say can I look at, if I do some calculation, can I look and can I see what does that result functionally equivalent to? If it's functionally equivalent to any of my numbers, then I know that that is definitely a number. Everybody agree? But the question is, how do I move from one number to the next number? Right? That's actually one of the key properties of numbers. You give me any number, I can always give you the next number. It's pretty trivial, right? Maybe you never thought about it too deeply, but every number has a successor, right? The successor of 1 is 2, the successor of 2 is 3. But we can actually define this using lambda calculus. So this looks kind of tricky, but it looks like it takes in 3 parameters, but it actually takes in 1 parameter. We want the successor. So let's say I give you, a successor function, what's the type there? What should it take in? What should it return?
A number and a number.
A number and a number. So it take in one thing and return one thing, right? So it takes in one thing, n, and it returns something of the form what? Lambda f dot lambda x, which is a function that takes in 2 parameters, which is the same type as the numbers we're talking about. So you think of it takes in some number and it returns arbitrary numbers here. So, but the question is, okay, does this actually work and what does it do? Right? So what is this function doing in here? So we have an f, then we have n f of x. So what's n here? The initial number. number that we pass in. So if we pass in, what was our numbers, kind of what do they do? They take in two parameters, and what do they return? So they take in an f and an x, and what is the body?
A recursive.
Not quite recursive, right? Because it's a fixed number of times. But it takes the first argument applied that many times to the second argument, right? F of f of f of f of f of x, right? However many times. So, if n is 1 here, it takes the first argument, it applies it to the second argument once. So it's going to return f of x.
Which is just adding 1.
And then we add one more f to it, which is 2, f of x. And then we can do the successor of that. 2 f's would be f of x, and f of x. This gives us 3. And similarly with 0, the successor of 0, so here we pass in 0 for n. 0 returns its second argument, which is just x. Right? So it's going to be lambda f dot x dot f of x, which is 1. And we can do this with 1, so we have the successor of 0 is 1. And based on how we define the numbers, we can do this. We can do 1, we can say what's the successor of 1, we substitute in 1 here, and then f is going to be applied to x that many number of times. And this time it's going to be 1, so now this is the same thing as f of x, which is 2. So the successor of n is always going to return n plus 1, based on the way we define the numerals here. And we can generalize this to, you can actually do this for addition. So there we were taking in one number and returning the next number. Here we're taking in an n and an m, and we are adding them together. I'm not going to go into the details here. I'll briefly go over it in case you're interested, that you can show that you can actually do addition like this. You can even do multiplication, so we can multiply two numbers together using our add function, right? So multiplication is just add something to something else that many number of times, right? So we can use multiplication here. And so here you can do subtraction, all kinds of crazy stuff with numbers. So you can completely do it representing everything just as functions, right? We have loops, right? We have logic, we have arithmetic, we have loops. Everything you need for a super cool, fun programming language. I see you all agreeing with me. And now, it saddens me, we've reached the end of the course. Yeah, so I kind of touched on it a little bit. Really the purpose of this course, and honestly the purpose of your computer science degree, is to dispel any notion in your mind of magic. Right? Computers are not magic. Trust me, I'm a huge Harry Potter fan. But magic is for Hogwarts. Computers are not magic. There's absolutely nothing magical going on. Right? It's all systems. It's all... We've studied compilers and how compilers work and how languages work, right?
The magic is understanding them.
No, it's not magic. It's just hard work. Just like anything. Right? So what you should take from this is that you have the faculties and the tools to understand these systems, right? It may take time, it may take effort, but you studied all about how a compiler works, right? You know all the steps that are involved in a compiler. Now you know if GCC is throwing some weird syntax error, you're like, oh, it's probably because it's expecting some token here, and it got a token that it didn't expect, and that's why it's throwing this error, so I should figure out maybe what's going wrong, right? And just like you take operating systems so that you understand operating systems, we built these things, right? Humans. We built these. You need to be able to understand them and to know that there is no mysteries, there's no magic. It's all computing all the way down to the silicon. So, go forth and do awesome stuff.
Go forward and do some stuff. There we go.
We'll miss you.